You're on. Thank you.
Okay, this presentation is a little bit different from some of the others here. I'm going to be talking about the problems with modern physics when you analyze it with logic. I'm going to show that all of the known theories of modern physics are known to be incomplete and therefore not true. I'm going to show that no two of them can be combined to describe an atom, an elementary particle, a nucleus, a molecule. And I'm also going to show some other things about fundamental theories. They cannot have the same fundamental constants and things of that sort. And then we're going to look at that and determine what direction should science be going. And then I'm going to show what happens if you do that. So that's what we have in mind. So we'll now proceed. Bottom button. Okay, first of all, the trouble with physics.
No, your microphone needs to be close.
Oh, the trouble with physics. The first one here is a book by Lee Smolin, which has been part of the politically correct establishment. And here are some of the problems with physics. We have created, oops, the top one goes back.
The middle one goes back.
The middle goes back, okay. We have created a lot of elementary particles.
Microphone up to your mouth, please.
A lot of elementary particles to, for instance, to mediate the strong and weak interaction forces and many other things, but they've never been observed. I'm an experimentalist in the field. I've worked for many years in accelerator laboratories, done all kinds of experiments. We don't observe them. We don't observe dark matter either. And we don't observe dark energy in any experiment that we do in a laboratory. We have created, in order to rescue general relativity theory, we have created dark matter and dark energy making up 96% of our universe, but we've never observed it.
Here.
We have unobservable black holes, and I think Ed Dowdy, who's here, will show you that the data does not support the existence of black holes. You don't see what you're supposed to see. And we have come about with the idea that there are multiple universes. And then we have our string theories to tie it all together, which have 8 to 11 dimensions, of which we've never seen. We have 19 to 29 adjustable constants in our string theories, representing unknown physics. How good is a theory with 29 adjustable constants representing unknown physics? I mean, couldn't we do better than that?
Yes, here.
You want more? Yeah. I know, but I'm just giving a few. Now I want to look at some of the assumptions of natural philosophy. This goes all the way back to the Indian Jains and the Greeks and those type people. One of the ideas is the idea of determinism, that there are natural causes for everything that happens in the universe. The second one is objective truth. Observations of the universe can be made independent of the observer. And 3, consistency. The same cause produces the same effects everywhere in the universe. This is where we started out with. All 3 of these are currently denied by modern physics. So that's not too wonderful. Now, I want to spend a moment on the axiomatic scientific method. This is the method that was developed by Euclid in order to do geometry, and basically it shows the role of logic in natural philosophy, in the scientific method. And as you'll see on this chart, you either observe patterns in nature and you apply inductive logic and come up with an axiom, or by intuition you guess an axiom. You take all your axioms together and you apply deductive logic to get your theorem or your theory. So that is what Euclid did. And did people like it? Well, all of the academies in Greece had a little motto on the door at the entrance. And I'm picture of the entrance, but this is an academy, what it looked like. And that said, let no one ignorant of geometry enter here. And that's because the axiomatic method that Euclid defined, or doing a proof, was considered the way to do all of natural philosophy, not just geometry or mathematics, but physics, gravity, electrodynamics. So all of these areas should be done that way. Now, let me go back to first. When they were doing that, oh, by the way, what is the most successful book in the history of science? It's Euclid's book. Euclid's book has been published in more editions in more languages than any other book other than the Bible in the history of man. So somebody's paying attention to what Euclid had to say, and that's because they agree with it. They think it's right. Now, they had trouble though with the with doing things like physics. The ancient Greeks did, because they didn't perform experiments. If they didn't observe it naturally occurring, they didn't observe it. They didn't get their axioms that way. So they didn't make any progress in a lot of areas for a long time. But a fellow named Isaac Newton came along, and he said, I have the solution for this problem. You need to perform experiments. You need to perform experiments and find the axioms. And you need to express the axioms as mathematical equations, which are very precise, not just general ideas. You want to express them precisely. And so he said, what you do in every area of science is you perform experiments, you find what the axioms are, then you use the complete set of those axioms and you derive the most general version of that area of science. Now, in his day, not too many experiments have been done, but he was able to take the experiments of Kepler, or the observations of Kepler, and the empirical laws that he had designed and obtain the force of gravity and the force of inertia, which was his claim to fame, and he expressed these things in mathematical form. But they didn't do enough experiments to get that far, but later in the days of Maxwell, we started making more progress and performing more experiments. We did them in the area of electrodynamics, and there were 6 laws of electrodynamics, empirical laws that were obtained. And I need to show Newton's empirical scientific method. He uses inductive logic in order to obtain his axioms, but his axioms are not his theory. His theory is down here. And he says you should use these axioms and by deductive logic derive force laws. He says everything in the universe is determined by force laws. And so you keep doing that and test it to see if it's the universal force law until finally you find an area of science that enables you to discover the universal force law. And you notice he called his force of gravity the universal force of gravitation, but he knew it wasn't the universal force, but he used that name. Okay, so that's what he did. Well, in other people, when they saw the work that Newton had done, they said, well, he was so successful and he didn't do what he said to do in his mathematical principles of natural philosophy. Like, for instance, in the force of gravity, he invented something called mass. If you ask him what is mass, he says, well, it's a property of matter that determines the force of gravity between various pieces of matter. And but if you ask him, well, what is that? He would have to say, I don't know. And then you had his universal gravitation constant, and you had his the fact that the force of gravity was, what do you say, what conveyed the force of gravity from one body to another, you know, and he couldn't explain how that happened. In other words, if I were to touch you, if I waved my hand like this, you don't feel a thing. But if I hit you with my hand, you have a contact force, and you know what caused it. Well, there's no contact force that you see in the force of gravity, so what is causing it? How does gravity get conveyed? So he had these kinds of philosophical problems. He couldn't explain those things. And so people redefined the scientific method from what he had invented to work in terms of hypotheses. Forget about axioms and logic and all that stuff. We'll go with hypotheses. We'll make observations, we'll formulate hypotheses any way we can, and a hypothesis is going to be our theory if we have data that predicts that's consistent with it. But hypotheses are based on assumptions, postulates, axioms, which are not mentioned. And those can be falsified by logic. That's the reason why they were removed. It's too much trouble. Let's just go with our hypothesis. And we don't have to worry about whether it's true, because these people and those who developed the existential scientific method did not believe in truth or absolute truth. And a lot of this is coming out of the things like the Protestant Reformation, a lot of upheaval in religious circles, and a lot of people just say, we want to get rid of religion, the idea that there's truth, and that kind of thing. And so they modified it to develop this. Now, natural philosophers, not all natural philosophers after that time when we went to existential theory, which is what we have today. We have postmodern philosophy of science, but it's really existential with silos, separate silos for each area of science. So each area is independent. So for instance, if I'm a chemist and I discovered that the force between vibrating neutral electric dipoles is the force of gravity, that count. You're a chemist. It's in the chemistry department. We're in the physics department. They don't pay attention to chemists. And just because you get the exact value for the force of gravity and you have an explanation for how it works, that doesn't mean a thing. We go with Einstein's general theory of relativity, which has all kinds of assumptions and axioms which are not true. But anyway, that's what's happening. But there was a fellow, the last great, what I'd call natural philosopher, was Henri Poincaré. There's a picture of him there. And he developed a branch of mathematics called metamathematics. And one part of that is metatheory. And this is the logic of theories. How do I determine if a theory is true without even looking at data? By just looking at the theory, can I determine it's a valid or invalid theory from logic alone? And the answer is yes. And so that's what Poincaré did. Now here's what he said. Poincaré believed there was absolute truth, and one of the first postulates he did was no two fundamental theories in nature can employ the same fundamental constant, such as c, the velocity of light. Only fundamental theories can be true theories. No two fundamental force laws can have the same mathematical form, such as 1 over r squared, because they're not both fundamental. And according to the superposition principle, no nonlinear theories may be combined with other linear or nonlinear theories to describe a coherent, stable system, such as an elementary particle, an atom, a nucleus, a molecule, etc. Any theory involving light is incomplete if it does not include terms that are a function of both r, v, a, acceleration, and dAdt. A is needed because all matter is constantly absorbing and re-emitting light. All matter, everywhere in the universe. And everything in the universe is accelerating. There's nothing that isn't accelerating at any distance from us. We've never found anything that's not accelerating. And dAdt is a recoil. from emitting or absorbing radiation. Like if I shoot a gun, my shoulder feels the recoil, you know. And so all theories involving light, or C, must include these terms. What do we see? Well, let's go to the first one. No two fundamental theories can employ the same fundamental constant. This is the, oops. This is electrodynamics, Maxwell's electrodynamics. You'll see that it's defined in terms of the scalar potential and the vector potential, which are non-physical items. And you'll see that it involves C, which it should, because C is velocity of light, so electrodynamics is related to light, so it should be there. Special relativity uses C. So the space-time interval, see that? Quantum mechanics uses C in its energy quantum, E equal h nu, which is equal to h times 2 pi over c, 2 pi c over lambda. General relativity uses C in its field equation. So now we have 4 theories that use C. According to Metatheory, only one of them could be true. When Poincaré pointed this out in 1905, he said, I think the appropriate theory that should be using C is electrodynamics. Therefore, special relativity is invalid. It's not a fundamental theory. It's an approximation of some sort. And as a result of that, Einstein never received a Nobel Prize for special relativity. He never received a prize for any of his work. He got one for his wife because they wouldn't give it to his wife, they wouldn't give it to a man. But other than that, that's what happened. So let's look at another argument here. No two fundamental laws can have the same mathematical form, such as 1 over r squared. And we have the force of gravity, and we have the electromagnetic force are both proportional to 1 over r squared. So only one of these can be valid, going by the previous argument that the only force that could involve C is probably the electrodynamic force. It makes sense that maybe of these two, electrodynamics should be the principal theory. Now, we have another principle. It's called the superposition principle. It has to do with adding things together. And this requires that only linear theories may be combined to describe a system with coherence and stability. If it's not a linear, if the system does not have coherence and stability, you're not going to observe anything that's stable. You're not going to observe an elementary particle that's stable. You're not going to observe an atom or a nucleus or a molecule, or, you know, so anyway, so there's 2 properties a linear system must satisfy: the homogeneity and the additivity properties for coherence and stability. And I've shown them in this equation here. If you have something that's a function of multiple parameters, it must be dividable so that each one is a linear combination. Now, if we want to describe matter in the form of an elementary particle, atom, or molecule by combining electrodynamics, relativity theory, quantum mechanics, and the standard model of elementary particles, we must have something like this, and all of these theories must be linear. But we see here's the electrodynamic force. You see it's 1 over r squared. That's not linear. We see special relativity theory, and it contributes b squared over c squared terms. That's not linear. Oh, I'm sorry. We look at the Schrodinger equation for quantum mechanics, and it is claimed to be a linear equation. Linear theories cannot be combined with nonlinear theories, according to the superposition principle. We have Dirac's equation also, and it's a linear equation. So we have that. Then In the standard model of elementary particles, the short-range strong interaction and weak interaction forces governing beta decay are a function of 1 over r cubed to 1 over r to the 5th, because it's short range, making them highly non-linear. So, on the result of that, we cannot combine the major theories of modern science. Electrodynamics, we cannot combine quantum mechanics, special relativity, or general relativity, or the strong interaction or the weak interaction forces from the standard model of elementary particles. So where are we? What is the solution? Well, from the earlier arguments, it looked like electrodynamics was one of the possibilities, but in order for it to work, it has to explain everything, not just electrodynamics, but quantum effects, relativistic effects, strong and weak forces in the nucleus, all that kind of stuff. Okay, so this last argument is because everything in the universe is experiencing acceleration, every bit of matter in the universe is absorbing energy and radiating energy continuously. Every theory of modern science that involves light or C must include the R, V, A, and DADT terms. Do they? And the answer is special relativity is R and V. General relativity is R, V, and A, but it doesn't handle radiation, and it doesn't have the DADT terms. And Maxwell's equations is R and V. So all of them are incomplete. So so anyway, these are the conclusions. We see that electrodynamics is nonlinear, special relativity, standard model of elementary particles is nonlinear, quantum mechanics is linear theory. According to the superposition principle, no two of these theories may be combined to describe any system. Only linear theories can be combined. We only have one linear theory, quantum mechanics, but it involves C, which is a logical contradiction because the fundamental force of electrodynamics is more appropriate for C than quantum mechanics. And only one nonlinear theory is possible, and if that's the case, and electrodynamics is nonlinear, then it has to be the universal theory of force. We see that that's the conclusion we just came to, that only electrodynamics could be the universal force. And since none of the pillars of modern science contain R, V, A, and DADT terms, none are complete. Okay. Now, I want to announce that this logical arguments that I've just shown you have been proven by this publication of this book called The Universal Force, Volume 1, derived from the more perfect union of the axiomatic and empirical scientific methods. In other words, this book executes what Isaac Newton said you're supposed to do. So instead of doing what Heaviside and the followers of Maxwell did, using 4 of the 6 empirical equations of electrodynamics, this book uses all 6. It doesn't need to use special relativity. It gets the forces in the field in terms of R, V, A, and DADT, which no other theory does. It conserves energy, which Maxwell's equations do not do. And it then shows that all of the fundamental forces of nature can be derived from electrodynamics. And you get a superior version of every one. So for instance, we'll go through some of these things you can predict. First of all, this is the Maxwell's equations. It shows you the form of the force. See, it's a function of R and V, as you see there, using this improved electrodynamic approach with the energy potential, no relativity theory. This is the potential right here. Notice that the force here has the same terms as, like the first term here is right there, and the second term there is over here. And you see that the R and B terms of the so-called relativistic Maxwell's equations are obtained, but they don't come from relativity theory. They come from the other two empirical equations of electrodynamics, in particular Lenz's law. And so we get an entirely different explanation for electrodynamics, and we're able now, from electrodynamics, to describe the emission and absorption of radiation and the radiation reaction force. And currently, my son went to Caltech, and they've held international scientific meetings for a number of years trying to get a solution that can predict radiation reaction properly from theory, and they have not been successful. And that's the #1 physics college in the United States. And so if they can't find it, and we have found it, and we've gotten it right, we have done something that you can't do with the work that they've done in quantum electrodynamics. Here is the force of gravity that's derived, and by the way, the step-by-step derivation is in the book that I just showed the cover of, and I have some copies here if you want. This shows the actual value. The force of gravity is due to the force between vibrating neutral electric dipoles and other higher multipoles, but the dipoles are dominant. And this is just the dipole terms. And here you can see the A is the amplitude and the omega is the frequency. And if you write it in the notation you're familiar with, F, the first term is F is equal to big G M1 M2 over R squared. And this second term, which has a beta squared effect, produces a number of factors. And we'll see it causes a quantization of gravity. It causes what's called modified Newtonian dynamics and that sort of thing. Down here's the force of inertia, which has been derived, and it has two terms. This term has never been observed or never been identified before in a theory of inertia, and it causes some very unusual experiments, and I'm going to show you a video of one of those so you get a chance to see what that's like. Okay. One of the oldest laws in astronomy is called Bode's law. It says that the period of the planets are integer multiples of one another. So if I, this is the actual formula right here. P of the nth planet is equal to P naught, that's the period of the sun, and A is the semi-major axis of the orbit. And you can see a fit to the data there. And you can see that all of the planets fall very close to the predicted value from this formula. And that's what Bode observed. And neither Newton's universal law of gravitation or Einstein's general relativity theory can say anything about the quantization of the orbits of the planets. But it's not just the planets, it's the moons about the planets are also quantized. And here's an example of Uranus, and you can also do Jupiter and all of the planets that have a lot of moons, so you can get good data. And they all fit. It's amazing. Now, it turns out that Bode's law actually works on the universal scale, if you know where the center of the universe is. And so, Pete Tift is one of the first that did the analysis of that. You want references to his work, it's in my book. And basically what it is we're on the Earth, and we're 2 million light years from the center of the universe approximately. And this is he's counting the number of galaxies that are observed in terms of distance from the Earth. And you can see it's kind of random here, but if you replot it from the center of the universe, which is 2 million light years away, you'll see that they're peaks, and they're multiples of one another. And those peaks obey Bode's law. So now we see that there is a lot of data there. You also can do the same thing to organic molecules, and you can show that Bode's law holds within an organic molecule like DNA or proteins or carbohydrates or sugars. All of them can be analyzed by this technique and show that Bode's law holds on all size scales. Now, if you look at the data for a galaxy, you'll see this solid, these dark things are the data for a spiral galaxy NGC 2403, which is just typical. And a fellow named Mordechai Milgram, he discovered that Newton's law predicts this. Einstein's general theory of relativity predicts the same as Newton's law. But if you have a modified version of electrodynamics, you can predict what this solid line here has. So he discovered empirically what is called MOND, or modified Newtonian dynamics. We predict that directly from electrodynamic version of gravitational force. Not only can you predict that, but it turns out the luminosity versus rotational velocity can be predicted. And we are able, with the Mond-type formula that we derive, we're able to predict this result. So we can predict the rotational velocity. Now that's only a few galaxies, but here's 900. And you can see it fits very nicely in terms of the data. This is the quantization of galaxy luminosity and size. And believe it or not, you can see Bode's law again. And so it's really amazing what you can get from the electrodynamic version of gravity. And so we're able to predict this value that Mordechai had. He never could predict it. He didn't know what caused the modification, but he was able to write a formula for it with a constant. And we predict not only the formula, but the constant from pure theory, no fitting data. So that's amazing. Also, for Einstein's theory of general relativity, in order to try and explain these things, they invented dark matter and dark energy. And you can make a fit for a galaxy by producing a certain amount of dark energy inside of the galaxy. But after you've done that, it turns out we've done Pioneer 10 and 11 experiments, and we have measured the anomalous acceleration of Pioneer 10 and 11. And that dark matter does not predict this, but our theory of gravity does. So we're able to predict, without making any dark matter or dark energy, without any black holes, we're able to predict all of the observed data as far as we know from astronomy. Now, we haven't looked at every single detail, of course, but I mean the major theories. So that's a great piece of progress. Now I want to show a video, and this video is related to gravity and also the force of inertia. And I'm going to show you that, if I can get it to play here. This is Eric Laithwaite. This is Eric Laithwaite.
Experiment with a spinning wheel, a rather large wheel, 13 inches diameter, mounted in a ball bearing on a shaft 3 feet long. I'm going to hold it like this and swing it in a circle and lift it with one hand, but only when it's spinning. First of all, let me weigh it to show you just how heavy it is. As I talk, you'll see that lifting it is quite an effort. It weighs about 40 pounds, and I can't lift it any higher than that without a lot of strain. So now we'll spin it up to 2,500 revs a minute which point it becomes a live thing. Then I shall lift it 5 feet in 3 seconds by going round in a big circle.
Notice he's going to do this with one hand, his right hand.
Whilst I'm doing it, I shall talk to you, so that you can tell from my voice that I'm not under any stress or any time. I shall let go with my left hand, and holding this remote end of the shaft only, I shall lift the wheel through 5 feet, all on its own with no effort on my part. All I do is apparently just to steer it along the path that it's already decided it would like to go. Then there's the question of how you stop the wheel. At speed, that wheel has enough energy to throw itself 200 feet in the air. Did you notice that as it went round in a circle, there was no centrifugal force trying to pull my arm out sideways? Let's just do it once more. To save time, we've already spun it up. So here goes 40 pounds of wheel as light as a feather. This is not a conjuring trick. This is a fact of science. Watch it again carefully. A fact about a spinning wheel, so far, everyone has missed.
Okay. We predict that can happen because of the second terms in the force of gravity and the force of inertia. Those terms involve acceleration, which is involved in rotation of that disk. For presenting this, Eric Lathwaite had his membership in the Royal Society of London revoked. He had his contract with the British government to make the high-speed electric railroad, which is now in Japan and China, revoked because Newton was discredited. So be careful when you do something in science. Be careful. The repercussions can be significant. Okay, repercussions can be significant. Now, with regard to the strong interaction, short-range force, and weak interaction, short-range force, we do not have to predict those because NIST has recently measured, NIST is National Institute of Standards and Technology in the United States here. They've recently measured nuclear isotope data to 8 significant figures. All these theories involving the strong interaction were when we were measuring it to 4 significant figures. What happens when you measure it more accurately and you consider conservation of energy? There's no strong interaction in the nucleus. There's no weak interaction in the nucleus. There are no neutrons in the nucleus. Can you imagine that? There's no longer any data to support those forces. But they can all the data you can show from their data that only a 1/r² force is present in the nucleus. And it's an electrodynamic force. And we're able to publish the predicted masses and properties of all the nuclei, all 5,000 and some, which no current theory can do. You have the quantum shell model theory of the nucleus that's used for some, and then you have the liquid drop model of the nucleus, which is used for others, and we do better than both of them. And we have no adjustable parameters. No adjustable parameters. That's amazing. One of the members, Roger Ryden, I don't know if you know him, he's published with me some of the nuclear work, and a number of other people have published with me because that's becoming the thing. And by the way, if you're at a university, be careful. Roger Ryden was told after he published the first paper along this line at University of Virginia, don't come back, you're fired. So be careful. Now, what are the ramifications of a universal electrodynamic force? All elementary particles are entirely electrodynamic. All atoms are entirely electrodynamic. All nuclei are entirely electrodynamic. All molecules are entirely electrodynamic. Life is entirely electrodynamic in origin. Medicine for disease can be administered electrodynamically without any chemicals. And people have been doing this in Europe, but it's against the law here in the United States. Also, the electrodynamic energy of the stars and galaxies can be converted to usable free electric energy anywhere in the universe. We have companies that invented these type generators in America. The government sent troops, surrounded their factory and warehouse, and has not let anything out for 20 years. But they're making them in China, they're making them in India, and they're giving them away to their people. But if you buy one over there, they will arrest you and try to come through customs and put you in prison. So be careful. There's a lot of politics. The energy and gas and oil industry does not want this to come because you will no longer need gasoline for your car, your truck, your airplane, your boat. You will no longer need gas or electricity from a utility company for your house. You know, it's just a lot at stake economically. And but that's part of this major reformation that my group at Common Sense Science is getting ready to make a worldwide announcement. We don't know what's going to happen to us. We do, but we're going to make the attempt. And we are publishing a series of books. The first book I showed you, I have some copies here with me. There are 4 more books in the series, and the papers on which the books are being written have already been published in various scientific societies around the world, but not all in one, so people don't see them all in one place. A lot of them are in European journals, because the European journals don't cause us the same problems as an American journal. I spoke about this 2 years ago in Baltimore at an international scientific meeting of the American Institute of Physics, and when I presented it, there were so many complaints from the Nobel Prize winners who were also speaking. I was an invited speaker at the meeting, that they asked that it be stricken from the record that I ever attended. My paper should not be put in the proceedings and taken out, and no one could pick up the proceedings there. They had to reprint them, and that's what's going on in this world. So be careful. And so the other thing I want to close with is, if you have a universal force, it's going to have a relationship to religion. And it turns out that there's a unique symmetry to the universal force. Every elementary particle, every atom, every nucleus, every molecule has that symmetry. Every crystal, every plant leaf, every plant flower, every animal body structure, like our cells, our skeleton, the structure of the orbits about the sun, and the structure of the orbits of the moons about the planets, the overall structure of the Milky Way galaxy, and then the overall structure of the universe, all have this symmetry. And that symmetry, according to the Bible, is the symmetry of the Godhead and the symmetry that was in the tabernacle and the temple. That was based on a heavenly vision that Moses and Solomon had before they built those buildings, those structures. So it's interesting, there seems to be a correlation between that and in the Bible, the mechanism by which God acts is electromagnetic. Look at it closely, you'll see it from the day of creation to all the way through to the end. Okay, I think that'll stop at this point.
Hey, that's
Time
it.
for questions. Again, we're running a little bit late.
Yeah, I got one.
Okay, I'll try Dave first and then.
The electromagnetic, the gravitational explanation using electrodynamics seems to be akin to the effect where you have all the particles that are positive particles in the universe repel each other, and all the negative charges repel each other, but positive and negative charges attract each other. But there's a residual effect. Seems to me that residual effect is what that equation that you just showed up there. That's the residual effect that explains gravitation. Could I be right in saying that?
Well, we derive it directly. We just take two vibrating neutral electric
Right.
dipoles, and we calculate the force between them, and then we average it over all angles and
The
directions.
residual effect. And
So
that's-
if it were just like electrostatic,
Mhm.
it would average to 0.
Mhm.
But it turns out if it's vibrating,
Yeah, right.
it doesn't average to 0, and it's always attractive.
Yeah, it's attractive, and it's
And,
gravitation.
So that's an
Now,
interesting thing.
what-
And we didn't discover it, chemists did.
Right.
They use it in their chemical factories. If they don't take that into account, they don't produce the quality
Right.
and the amount of the chemicals they're making
Now,
in their
you might
factory.
be interested to know that one of the ministers of my church, I've been teaching Bible prophecy in my church, and she came up to me and just blew my mind, man. She was talking about the only way you get to heaven, you got to go by Jesus first, and you have the spirit be drawn. Gravity is a drawing force, right? And she talked about this gravitas. I never thought about that before. You ever
Well,
thought about that?
I'll just tell you one thing. Faraday and one other of the principal investigators of electrodynamics called the electric field the
Mhm.
spirit,
Mm-hmm.
because they saw a lot of similarities.
Right.
And but they didn't know everything we know today, but they had that idea in the back of their mind. Okay, yes, sir.
My question is about the energy that is within an atom.
Uh-huh.
And I'm trying to picture it in a physical sense. And my question is this: is that energy the vibrations
Uh-huh.
of the particles that constitute the atom?
Yes, and as you know, a vibrating dipole must radiate continuously. Okay, and what happens when it radiates? It goes down. The vibration gets smaller, and so it turns out that the cosmic background radiation is the radiation primarily from hydrogen and helium, from the vibration of the dipoles in those, and it's down to a certain so many degrees Kelvin, and so I calculated to see what was the magnitude of the vibration, and it turns out it was about 1% of the distance between the electron and the proton in that typical atom, like hydrogen. And so that was interesting. And all of them are doing that, but if there was something like a creation, like when you go, Halton Arc has shown some data where you have a quasar created in a galaxy, and you see that the redshift is quite different from that because of this, the structure is new and it hasn't decayed yet as much. And the gravity is decay. That's why there is no agreement between experimentalists on the value of big G more than 3 significant figures, because every measurement that's made is different. But when I'm doing atomic nuclei, I can measure them to 8 significant figures, and everybody agrees who reproduces the experiment. So something is happening with gravity, and we're not taking into account electrodynamic effects, we're not taking into account the decay, and the decay of gravity is causing the Earth to expand and the continents to come apart, and it is the explanation for how the plates are actually moving on the surface of the Earth. And I have a whole talk on that, but this is just one of about 80 talks that I do. And, but this is the beginning one to give you the overview of the picture. Yes, sir.
Quick question. So, with an expectation that electrodynamics might be something that actually incorporates the electromagnetic dynamics that you have been taking as a basis, I would ask you how your theory would relate to the Occam-Razor's principle of simplicity and kind of.
Okay.
Could you think that there would be some kind
If
of
the
really
electrodynamic force
simplification to
is
get
the
back
universal
one step?
force, there's nothing else. There's no ether separate from electrodynamics. And so, but Arthur Compton's last graduate student named Winston Bostick was able to perform experiments and show that elementary particles are made from standing waves called solitons in the electromagnetic field. So mass is not fundamental. The field is the fundamental thing in the universe. And all elementary particles are made of solitons. In my theory of elementary particles, I build all of the stable elementary particles out of solitons. I show the structure. It's the same kind of structure. You have the atom and the nucleus, and you have for galaxies and that sort of thing. The scale, every symmetry of electromagnetic force is displayed on all size scales, even within an elementary particle. And so,
Solitons real?
solitons are real. They're the strongest known items that man has ever experimented with. If you make a controlled thermonuclear fusion reactor, after a while, the material that you built the reactor out of crumbles because of the radiation it destroys it. But that radiation does not affect a soliton. It is stronger, many orders of magnitude stronger
So
than
what
an
is the
atom
form,
is.
the dynamics, the topology of the
Soliton?
solitons?
Soliton is a toroidal ring
Oh,
structure.
okay.
And so,
Do you have an ultimate, or do you believe in partless parts?
pardon?
Do you believe in partless parts, or is it infinitely down?
Well, everything is made from the electromagnetic field, and the solitons that make them, out of which all elementary particles and atoms and nuclei are made, they are created by various forces in the electromagnetic field. If you have there's a very nice video, but I don't have time to show it today, but you can get to it on YouTube. If you look for solitons in water, you'll see someone at a swimming pool takes a plate, pushes it into water, and you make two solitons. These are water solitons, not field solitons. And they are always made in pairs. And just like the solitons in nature are also made in pairs. And there's a problem in the standard model of elementary particles. Why are there only real particles and not antiparticles? Why don't you have equal number? Well, really, the soliton and anti-soliton are what you have. And if you look at all elementary particles together, you have an even number of anti-solitons and solitons. So you answer that question, which elementary particle people have never been able to answer.
But are solitons made of something?
Yeah.
Solitons are made of the
Okay,
field.
ma'am, ask just one quick comment
Charge.
regarding your question and this answer.
Okay.
I mean, here maybe if one just think of the kind of recycling procedure, kind of that those maybe some most elemental structures structure themselves in more complex and so on until galactic and other levels, and then out of them, from their centers, from those like accretion disk, where only recently the physicists admitted that they are really still emitting something. That actually we are getting back that very basic material.
I understand.
And then can we recycling? That would be something that would be pretty satisfying to everyone, I guess.
No, because to me, I don't believe there are partless parts. I can't see the universe having something that's the last thing.
Yeah,
That's
yeah,
what I'm
so-
saying.
so-
I'm just, I'm not,
yeah.
say, I'm not.
Yeah.
The model's
Yeah, yeah,
fantastic.
yeah.
The equations are amazing.
So-
I was just asking that one
Yes,
question.
so maybe we may not be even should not want look into that very basic. just if we say, okay, we are getting back again, so if we're up to something, maybe it's possible to get down there, but not in the way that you are breaking those whatever small level structures and then hand hunting for the particles
Okay.
parameters and so on. Thank you.
We are also following Occam's razor. We have simplified all of science to just electrodynamics. Now, I didn't have a chance to do it, but I have a whole talk on light
Yeah, but maybe
and
that
medicine
form,
and all that.
maybe that form of equation should be
Right.
maybe a little bit simpler.
The-
Like,
the-
that's
the-
my point.
The soliton is just your method of getting the solution to all of the results that you have, right? Even though we don't have a way of seeing them, you know, we
Oh,
can't
yes, we do.
visually see it, but you can.
Winston Bostick made
Yeah.
them, he photographed them.
Mhm.
We put them in jet planes. We put energy into the soliton.
Right.
We wanted to see how many millions of degrees of energy it could hold,
Mhm.
and we could not exhaust it.
Right.
And we could, if you had a structure made of multiple solitons, we could break them apart.
Oh, I see, yeah.
But we
Okay.
couldn't do anything in terms of completely annihilating them, although a soliton, anti-soliton can annihilate one another.
Right. What do you mean annihilate?
That means it's the same thing as you do in a swimming pool. If two of these solitons that have opposite rotations, and by the way, the rotation is opposite in the rings when you make them on a swimming pool. When they come together, they can annihilate one another.
Right.
But I can make a separate wave on the side that goes over and covers them up, and you think, oh, they're gone, and then they come out the other side,
But
and they're still there.
why they should not be put, at least in the ether as a subset, put close to each other, we get them integrated, and then they get another stable structure.
They're made of the field, is that what you're
They're made
saying?
of the
It makes
field,
something
and the
missing,
field is what
something
we would
missing, yeah.
call the ether, but the field is attached also to matter, because these particles, which are standing waves, the standing wave has not a small thing. The soliton is not a small thing. It extends out to great distances. So when you take that into account, what you have to do is look at the local environment and when you do an experiment, because it's going to affect most of what you measure. And so that's what we are doing, and we're able to explain the Michelson-Morley experiment and the ring laser experiment, where one can measure the velocity and the other can't. And we explain why that is.
Okay, we're going to have to cut it off, folks, okay? Thank you very much.